All right. Hi, everyone. My name is Snyder. Thank you for coming today. My presentation is about application development for wastewater distribution networks for asset management. So to start us off with some background, it's been about 50 years since the Clean Water Act, and most of the wastewater industry hasn't seen a lot of upgrades since then. The Clean Water Act saw a lot of retrofit. I'm sorry, say what? Back? Closer. Oh, it's not coming through? Okay. Oh, move the mic. Oh, okay. Anyway, so most of the wastewater industry hasn't seen a lot of their assets rehabilitated or replaced ever since then. This was 1972, so a lot of them are aging. On average, wastewater infrastructure assets last 50 to 100 years, so it's pretty relevant at this point. Since then, they haven't had a lot of funding to replace and keep up their assets. Just last year, there was a funding gap of $257.5 billion. You can see the distribution broken down by state on the right. Now, because of these reasons, the current state of the conditions of the assets, they are prone to failing. And when they fail, there's a lot of detrimental effects on the environment, the economy around it. Obviously, you're spilling toxic material into the environment as soon as it breaks. And in addition, I mean, I'm sure we've all seen a water main break. So that could happen on any road. It could disrupt traffic, and it disrupts sewer service for an entire community at large. Basically puts things at a standstill. Because of the current affairs and the funding gap, the American Society of Civil Engineers recently gave the wastewater infrastructure a rating of a D+ in 2021, which is a far cry from its B- acceptable standard. And this rating's seen little improvement for 20 years. So, and also, in addition with this, their lack of funding makes it hard for them to even proactively look at their assets because what the technologies they use, such as ultrasounding, sending a gauge through the pipes costs tens of thousands of dollars per mile just to do, and a lot of time on top of that. And you can't just dig up a pipe and look at it and say, it looks like it works. I mean, that's not going to help you much in the long term when it comes to managing your assets. So their asset management plans have become very reactionary, fixing it when it breaks. But what's an asset management plan? An asset management plan is a stepwise process. You take your asset inventory, you assess how it performs, how it fails, and how much it costs over its lifetime, set the level of service you might need, optimize your costs, and you build your asset management plan with these pieces, updating as you develop your inventory. But steps 2 and 3 tend to introduce bias because old engineers might have different opinions as to how an asset could perform as opposed to a new engineer. And also, costs differentiate between different models that you might be using to model these assets, and these engineers have different experience with different models. So to resolve this bias and this inaccuracy, we've developed a tool for this asset management that minimizes the bias. We are using computational tools in place of that human judgment to make correlations in asset data, and from there, those correlations could be used to develop corrective actions for a utility company. You have your inventory, input it into a predictive model that provides a risk assessment that is viewed in an application. That application suggests corrective action to the user, then they can act on it to redevelop their inventory, and the cycle repeats just like the process you saw last. To do so, we will need a framework. So we've devised a 3-phase framework to get this tool up and running. Starting with phase 1, we have inventory input and data preprocessing. We're getting our data, and we're trying to make sure it's fit for our model. So to do so, we've partnered with the Atlantic County Utilities Authority, the AIChE. They're a wastewater utilities company that serves 14 municipalities in Atlantic County, and their facilities treat 40 million gallons per day, relying upon over 60 miles of wastewater infrastructure assets. 68% of those pipelines make up the data we're forming our model with. As you can see in the table, there's a lot of variation in the data they have. Their segment lengths could be as little as 15 feet to about 7 miles. They have 2 different flow types, gravity-driven flow, force-driven flow, and their pipe materials, they have 8 different pipe materials going. So there's a lot of variation to work with and a lot to take account of. So now that we have our data, we can move on to making our model itself. To make that model, we are using random forest classifier in Python. And our model is composed of 2 different variables, the risk probability and the failure impact. As implied, the risk probability shows how likely will an asset fail at its current conditions, and the failure impact is how much will that failure actually impact its environment. You can see in the table that there's different factors involved. The first 3 for both are actually the same, but as you move on, they differentiate between the 2 to reflect what they were trying to say. There's more material in downstream pump stations, for example, so there's going to be more release into the environment for failure impact, just as an example. Now, the product of these 2 variables is our overall preventative measurement number, the OPMN. It is our decision variable that tells us how important is this asset to rehabilitation. 1, not that important, you can let it go. 25, it might break tomorrow. So the largest contributing factor is what is going to inform our corrective actions for our model. When testing this model against ACUA predictions, we found that the risk probability has an accuracy of 99.2%, while failure impact had an accuracy of 95%. You can see in the table that there's very little deviation between their determined OPMN scores as opposed to our models. So now that we have a reliable model, we can move on to actually creating the application we're using for wastewater industry as a whole. So to do so, we've included some demonstrations. The first tab you're going to come upon is our Pipelines at Most Risk tab. It is intended to give you a quick rundown on what pipelines are most important as sorted by descending OPMN score. No. Sir, is the video in there? I updated the file. Oh, okay. Well, okay, I'll go without the video then. So basically in this, there's a text box at the top where you can change the amount of pipelines you would like to see. It could be as little as 5, as large as 20. And doing so, you can view in the entire database, you can view as little as you'd like. This is still under development. That's why they don't actually have their real names right there. But the Generate Report button is intended to export an Excel file that will show a breakdown of the average contributing factors across the whole pipeline. Now, moving on to our second tab, the Pipeline Database tab, there are several different features, but the functions of this is to be both a way to search your database and a way to manipulate it. So in the very top is the search function itself. On the left, you'll see a drop-down menu where you can search through all the different categories and properties of asset data. From there, you can type in some kind of value you'd like to search, press search, it updates accordingly. Same with the reset, you can reset the view to see the entire view. It can search both numeric and non-numeric data. More importantly is the actual way to manipulate that data. In the bottom, you can have different settings. You can change the material, you can add an asset, delete it. If you want to just view the data, it grays out all the boxes so that you can't actually alter the data by accident. And from there, you can change pipe materials, diameters, the town it might be in. You can add a new asset entirely and delete it accordingly. So to the next tab, our Model Information tab. This shows you how the model is functioning as a whole. In here, you're seeing a breakdown of the different factors that contribute to our models. On the left is our base model, while on the right is a model that we can make from scratch. So you can't alter the base model as it is. Obviously, it's set. However, on the right, the wastewater utility company is able to input or delete variables and see how these factors would contribute. Now, unfortunately, I did have this included on the video, but it's not displayed. Another feature of this tab are confusion matrices. Confusion matrices are essentially a way to predict the accuracy of the model. So if you can just follow and visualize with me real quick. So on the y-axis, there are the truth values, meaning that what are the actual values that this is supposed to be. So that would be represented across. And on the x-axis are the predicted values. So when these line up, the main diagonal of the matrix, that is actually the accurate prediction, meaning the model is predicting the same as it should be. Now, the outliers are any numbers that would be outside of that main diagonal. So by altering the different factors you have involved, you can see how it performs with the makeup and the accuracy of the model, meaning that it is flexible to any wastewater utilities company that would like to use it. As an example, in the video, what I end up doing is I take out pipe size in this, and it actually changes the entire makeup of the feature importances. It reruns the model from there. While it has it there, I put in remaining life, and before then, if I remember correctly, flow rates was the most important factor, but then it gets replaced with the remaining life as it reruns the model. In the confusion matrix, putting remaining life actually improves the accuracy of our model, so it's a quick way for us to see what factors we want to update the model with, while taking out the pipe type number value and the risk probability actually decrease the accuracy of the model. Sorry for the lack of demonstration. So now that we have our model that can give a risk assessment and give corrective actions, and we have a visual application that can assist in the asset management plan formation itself, we are going to be moving on to some rehabilitation optimization for those predicted corrective actions. Now, the corrective actions are still in the works. We don't have the costs associated yet, so they haven't been actually implemented in a working form to the application yet. I apologize. But this entire design is supposed to take you from start to finish with your asset management plan while optimizing your costs forthwith under the limited budget that wastewater industry is already under. This work was done with my team, our graduate advisor, Curdy M. Yankee, our graduate mentors, Jake Stengel, Emmanuel Aboji, and our undergrad team consisting of myself, Quentin Nathaniel. I'd like to thank the American Institute of Chemical Engineers for allowing me to speak today, and I'd also like to thank NJIT for hosting the event here. I would love to thank the AIChE for giving us our data, funding our work, and the chemical engineering and civil engineering departments back at home in Rowan for helping us with our work. My email is shown on this slide, and if you'd like to see any other projects we're working on, the email is at the bottom. Thank you. I can take any questions.
I have a question. So I have many, but you started showing that you validated your model before you started using it as a predictive tool, right? And my question is, how many data points did you have to predict to look at that validation?
So the AIChE was able to provide us with 300 different segments and so they had these assets actually in an Excel sheet, but it wasn't formatted in a very linear way that our program could read it. It being Java, it can't look at it the same way that we do. So we had to reformat the 300 data points by hand, into a new Excel sheet, which then can be automated and programmed with.
So about 300 then, right?
Yes.
And how many parameters are in that model that you're looking into?
Parameters. I'm going to estimate, I don't know the number off the top of my head, but it's greater than 15, less than 30. So there's a lot of different parameters we're working with. I'm going to say about 20 or so.
So you think that's enough data for that many parameters?
Well, there's a lot of variation, so I'd say yes, especially if it's predicting close to what the AIChE is given their history.
Hi, good presentation. I have some clarification questions. First of all, what do you mean by failures?
Failures?
Yes.
So the obvious things such as a pipeline snapping, as it does, but we had a case study actually where at the Bader airfield, they had a main break that spilled, I think, somewhere between tens of thousands to about, there was a lot of gallons of wastewater just coming out into the bay. So failure is basically when the pipeline that we're studying right now, because that's the data we have, it's when it breaks, when it cracks, and it leaks into the environment.
Great. Then what are the important pipe parameters that you guys considered in your models? When you say different pipe type, what are those properties of the pipe?
The pipe types?
Yes.
So we can't, obviously it's very generalized like asbestos concrete or vitrified clay. We don't know, we can't go to the manufacturer and ask exactly how they made it. However, they are different materials. So the point of the machine learning program is to take the fact that we don't know the specific, the specifications of the material itself, because they were made at different times with different methods, possibly different companies, but we can make correlations of the general type it is, such as steel, HDPE, again, vitrified clay, asbestos concrete, although that's getting phased out. We also have thermoplastic composite pipes. They're extremely different materials, but they're all part of the same pipeline. So the way to tie it all together was that asset correlation.
Thank you.
Yes.
All right. Hi, thank you for the talk. So I was wondering if you could talk a little bit about your model development. How did you arrive at this particular random forest model? Did you try other models, hyperparameter tuning?
So we did do some research into different models, and the reason why we didn't want to use some others is because the other ones like neural networks and most of them really couldn't handle the smaller data set we have. Usually when people use machine learning to form correlations, there are thousands of data points. There weren't thousands of pipes, so we couldn't just come up with pipes and pretend that that would work. So we used random forest, because what random forest actually does, I don't have a slide, but visualize with me here. You have a set of data, it finds what factor actually differentiates them the most out of a random set of factors, and it repeats this process until it can separate them properly and see which correlation separated the most. Therefore, that factor is the most important in showing how it performs. The depth of the tree, how many decisions it comes across, is directly related to its accuracy. So that accuracy slide you saw before, Alice, go back to it real quickly. This actually means that they are very deep trees, and the fact that they're predicting close to what the AIChE is given means that this random forest is functioning well with our limited data set. So that is why we are using it. It's because of more of its applicability than anything else. Am I out of time?
Okay. Can I ask one more short question? Do we have time? If not, it's okay.
Yeah, I think time is
Yeah,
over.
that's fine.
Sorry.
All right, thank you.
Thank you, everyone.